If you've ever heard that faster fluid means lower pressure, you've heard Bernoulli's principle. But that explanation is incomplete, and in many situations, it's actually misleading. In this video, we're going to break down Bernoulli's equation properly, where it comes from, what it really means, where engineers use it, and just as importantly, where it completely fails. On Engineeringness, we're diving into everything you need to know about Bernoulli's principle. What is Bernoulli's principle? The principle is named after the Swiss mathematician and physicist Daniel Bernoulli, who published it in his book Hydrodynamica in 1738. Bernoulli's principle is often explained by using the following statement: as the velocity of a fluid increases, its pressure decreases. However, this statement on its own is incomplete and often misleading. The correct statement is that for steady, incompressible, non-viscous flow along a streamline, the total mechanical energy per unit volume remains constant. Bernoulli's equation is therefore fundamentally an energy conservation statement applied to fluid motion. Let's imagine forcing a liquid through a narrow opening in a pipe. As the pipe constricts, continuity requires the velocity of the fluid to increase if density remains constant. If no energy is added or removed from the system, Bernoulli's equation predicts that this increase in kinetic energy must be accompanied by a decrease in static pressure. As the pipe constricts, this creates an area of lowest pressure at the narrowest section of the pipe, known as the Venturi throat, which entrains or pulls in the surrounding atmospheric air. This is known as the Venturi effect and is something we will discuss later on in the video. Bernoulli's equation helps relate pressure, velocity, and elevation in a flowing fluid, but it does not independently explain all fluid motion. In many real systems, conservation of momentum must also be considered. As it flows, three things change: velocity energy, the kinetic energy of the fluid; pressure energy, the pressures the fluid experiences; and the potential energy, the height or elevation of the flowing fluid. Due to conservation of energy, the sum of pressure, velocity energy, and height energy remains constant along a streamline. So if velocity increases and height is unchanged, pressure must decrease. Bernoulli expressed this relationship in what's now known as the Bernoulli equation, showing how velocity, pressure, and height energy balance along a streamline. P plus 1 half rho v squared plus rho g h equals constant, where P equals static pressure, rho equals fluid density, v equals fluid velocity, g equals gravity, h equals height above reference. This is the Bernoulli equation, the foundation of fluid mechanics. Each term represents mechanical energy per unit volume of the flowing fluid. Think of the equation as three energy buckets. The first term in the equation is the static pressure of the fluid, P. This is the force the fluid exerts on the walls or surfaces. The second term represents the fluid kinetic energy per volume and is known as the dynamic pressure. As velocity increases, the kinetic energy term increases. Under Bernoulli's assumptions, this must be balanced by a reduction in static pressure or potential energy. The final term in the equation represents the potential energy or height energy and is known as the hydrostatic pressure. As you can see by the term G, this is the pressure exerted by the fluid due to gravitational forces. G is the gravitational acceleration, which is 9.81 meters per second squared on Earth, and the h on the equation is the height or elevation of the fluid from a reference point. The higher up the fluid, the more gravitational energy it has. Before applying the equation, it's important to understand where it comes from. Deriving Bernoulli's equation. The Bernoulli equation for incompressible fluids can be derived by either integrating Newton's second law of motion or by applying the law of conservation of energy via the continuity equation. Assumptions of Bernoulli's. When deriving Bernoulli's, the following assumptions must be made. The flow is steady. Nothing changes with time. The fluid is incompressible. It has a constant density. There are no friction losses, so no energy is lost as heat. The first derivation we are going to look at is when Bernoulli's equation is derived by integrating the Euler momentum equation. Rho dv over dt equals negative delta p plus rho g. where ρ equals fluid density, v equals velocity vector, d over dt equals material derivative, acceleration of the fluid parcel, negative delta p equals pressure gradient force, ρg equals body force due to gravity, which itself comes directly from Newton's second law applied to a moving fluid. Force per volume equals mass per volume times acceleration. Imagine a small element of fluid moving along a streamline. Three forces act on this fluid element. Pressure forces pushing the fluid forward and backward, gravity acting on the fluid mass, the inertia of the moving fluid itself. Applying Newton's second law along the streamline gives the Euler equation. When this equation is integrated between 2 points in the flow, we obtain half v squared plus p over ρ plus gh equals constant. Multiplying through by density, or ρ, produces the familiar Bernoulli equation. Half ρ v squared plus p plus ρ gh equals constant. We can also derive Bernoulli's by applying the law of conservation of energy via the continuity equation. For steady incompressible flow in a pipe, we can show flow as the following equation. A1 V1 equals A2 V2 equals Q. This tells us that as the pipe widens, the velocity decreases. We can rearrange this equation to find the velocity on the second part of the pipe. We can then substitute V1 and V2 back into the Bernoulli's equation. The continuity equation comes from the conservation of mass principle. It states that mass cannot be created or destroyed within a control volume. The conservation of mass principle is denoted by the following equation, where the m with the dot above denotes the mass flow rate. This can be converted to show the mass flow rate of the fluid as the sum of its density multiplied by the cross-sectional area multiplied by the velocity of the fluid. ρ1 A1 V1 equals ρ2 A2 V2. Now, let's imagine a pipe with water flowing through it. The pipe has a change in diameter and elevation. As the water moves from point 1 to point 2, three things change: the pressure, the speed of the flow, and the height of the pipe. Because energy is conserved, any gain in one of these must come from a loss in one or both of the others. At point 1, pressure P1 pushes the water forward into the next section of pipe. At point 2, pressure P2 pushes back against the flow. So the net pressure force acting on the fluid is shown by the following equation: P1 minus P2. This difference in pressure is what we call the static pressure term in the Bernoulli's equation. The work done by this pressure difference supplies energy to the fluid. The pipe widens, the velocity changes according to the continuity equation. The kinetic energy per unit volume of the fluid is denoted by the following part of Bernoulli's equation: a half ρ v squared. So the change in kinetic energy from point 1 to point 2 is shown like this. Because point 2 is higher than point 1, the fluid must gain gravitational potential energy. Potential energy per unit volume is shown by the following equation: ρgh. So the change in potential energy is shown here, ρg multiplied by the difference between h2 and h1. Now we apply the energy balance. Pressure work equals change in kinetic energy plus change in potential energy. So P1 minus P2 equals half ρ v2 squared minus a half ρ v1 squared plus ρg multiplied by the difference between h2 and h1. Rearranging to collect terms at each point, P1 plus half ρ v1 squared plus ρg h1 equals P2 plus half ρ v2 squared plus ρg h2. And since this applies between any 2 points along a streamline, we write the general form P plus a half ρ v squared plus ρgh equals constant, which is Bernoulli's formula. Forms of Bernoulli's equation. Bernoulli's equation doesn't come in just one form. Engineers use different versions depending on what they're trying to calculate. The following table breaks them down. If you're enjoying this deep dive into Bernoulli's principle and fluid mechanics, Make sure to hit subscribe and give the video a thumbs up. We've got plenty more engineering foundations and real-world applications coming your way. You can also check out our online store for engineering-themed gear and tools that help support the channel. Every purchase genuinely helps us keep making high-quality content. And if you want to take things a step further, consider becoming an Engineeringness member. You'll get early access to new videos, behind-the-scenes content showing how we animate and build these breakdowns, and access to our members-only chat rooms, where we talk about all things engineering. Bernoulli's principle shows up in many real-world applications. Some of the main areas we can see this is when plane wings generate lift. Fluid flows over the wings faster due to the wing's design than the fluid flowing beneath the wing. This high velocity flow above the wing causes an area of low pressure and an area of high pressure below the wing where the fluid velocity is slower, in line with the principles of Bernoulli's equation. Lift arises from the pressure field created by circulation around the airfoil and the downward deflection of airflow, which involves conservation of momentum. Bernoulli helps relate velocity and pressure locally, but it is not a complete explanation of lift by itself. When a fluid flows through a pipe that narrows, the continuity equation tells us the velocity must increase, and Bernoulli tells us that when velocity goes up, pressure must drop. This pressure drop in the narrowed section is known as the Venturi effect. Now, let's say that we create a small hole in the pipework that is open to atmospheric pressure. The atmospheric pressure, which is higher than the internal pressure within the pipe, will cause the air to become entrained within the pipework. It is used everywhere in engineering. Venturi flow meters measure flow rate by comparing the pressures in the wide and narrow sections. It's how aspirators and eductors draw in chemicals or gases without using a pump. Limitations of Bernoulli's equation. Although Bernoulli's equation is extremely useful, it is important to understand where it breaks down and where it has limits. If viscosity is significant, mechanical energy is dissipated as heat and friction losses must be included. In turbulent flows, additional energy dissipation occurs through velocity fluctuations and eddies. In compressible high-speed gas flows, density changes become significant and the incompressible form of Bernoulli's equation is no longer valid. Across shock waves, entropy increases and mechanical energy is not conserved, meaning Bernoulli cannot be applied directly. Understanding these limitations is essential when applying Bernoulli's equation in real engineering systems. Bernoulli's equation is one of the most important relationships in fluid mechanics. It connects pressure, velocity, and elevation through conservation of mechanical energy. But as we've seen, it only works when its assumptions are satisfied. Used correctly, it becomes an incredibly powerful engineering tool. Used incorrectly, it can lead to completely wrong conclusions. If you enjoyed this deep dive, hit subscribe and give the video a thumbs up. Check out our online store to support the channel or become a member for early access and behind-the-scenes animation content. Thanks for watching and stay curious.